No, we're gonna do it. I'm doing that.
All right, good morning. Those aren't the right announcements, are they? I've had a heck of a time getting my files to upload. All right, well, I remember the announcements, even if they're not on the beginning slide there. The first announcement, I guess the main announcement you need to know about is that the homework you've just submitted, that probably won't be graded in time for you to know whether you did the problems right before our test on Thursday. So the solution for the assignment that you just submitted, that's available right now on Blackboard, so I'd encourage you to look through it, kind of self-correct if you notice that you made any mistakes compared to what the solution says and what you had calculated. So the exam that we're having on Thursday covers everything from Lecture 1 through and including today's class meeting. So it's essentially Chapter 2 and Chapter 3 in the book. And I've already prepared the equation sheet that you're going to use for the exam, and that's available right now on Blackboard if you want to take an advanced look at that. I'll print it out so you don't need to bring a copy of that equation sheet with you. The only thing you need to bring to the exam is a pencil and a calculator. Do you have a question?
Yes. Is the exam mix of concept and equation, or just pure equation test?
It's just problem solving.
Okay.
Are there other questions about the exam on Thursday? All right. So today we are going to do a brief review of buoyancy and then talk about stability of floating bodies. Stability of floating bodies is also the subject of next week's lab, so the two kind of fit together pretty well.
You mean today's lab? Or?
No, I mean next week's lab. All right. So just as a beginner, though, let's look at, let's say we have a submerged plane, and it's triangular in shape. Just to get a refresher on how we interpret drawings like this, remember that when you see something from the front view, you don't necessarily get the height of the object if it's inclined, like this one is. So why don't you take a moment and try and calculate the dimensions of the triangle, meaning the length of the triangle and the width of the triangle's base. Okay, I took an advanced look at some of the submissions for the homework assignment that you submitted today. I was just curious to see, which problems people did right, which problems people seem to be struggling on. And one thing I noticed was that when people did make mistakes, it was more often than not just a matter of interpreting shapes. It wasn't that you misunderstood the concepts of fluid mechanics, but maybe you were just having some trouble like visualizing what this object looked like in 3 dimensions. So it's certainly something that you can never get too much practice on. All right, so what we're going to do with this one is that we know the width of the triangle just by looking at it directly. From the front view, we can get an accurate representation of its width, but then this physical length of the triangle is the hypotenuse of a triangle, another triangle, where the base of that is 200 centimeters and then the height of it is 110. And so what you should get is that the physical length of the triangle is 228.25 centimeters. Oh, hold on. Did I do that wrong? It's 110, right? Looks like I've written 100 there. Is the answer right, but I just wrote the wrong thing?
Yeah.
Okay, well, let me fix that. That happens more often than I'd like. All right, so it's 110, but for those of you who did it right, the 110, the answer is still 228, right? Okay. So that's just a quick refresher there, and we'll have a couple others as well. Now today what we're going to be talking about is buoyancy and stability of floating bodies. So in the first of our two labs that use that floating pontoon apparatus, those of you, the civil engineers, will see it for the first time today. The mechanical engineers saw it yesterday. We're going to use it two weeks in a row, and it's floating in equilibrium at the top of the surface of water. Sometimes what we have to do is look at given information and find out whether or not it's floating in equilibrium as pictured. And so here's an example that asks, what are the buoyant forces that are acting on a barrel, where you're given the dimensions and you're given the mass of the barrel. And secondarily, it asks if it's going to sink or if it's going to float, because right now it's not in equilibrium. There is an imbalance between its buoyant force and the weight of the barrel. So give this one a try. See if you can come to a determination of whether it's going to sink or whether it's going to float. Okay, so we don't yet set the buoyant force and the weight equal to each other, because the problem statement says it's submerged, but it doesn't say that it's in equilibrium. So it could be sinking to the bottom as we get this picture. It could be in the process of floating to the surface, at which point it'll hop out of the water a little bit, and how deeply it sets in the water is partly dependent on the ratio between the buoyant force and the weight. So we don't yet know what the situation is, but what we're going to compare is the buoyant force and the weight, and then look at which of the two is larger. Okay, so we know that the buoyant force is dependent on the volume that's submerged and the volume of water that's being pushed out of the way by that barrel. So the volume is going to be the cross-sectional area times the length, cylindrical volume, and we get the volume of water displaced. And so the buoyant force that's acting on the barrel is going to be equal to the volume of water displaced multiplied by gamma. Another way that we could calculate the buoyant force would be to look at the weight of the water above the barrel and the pressure forces acting over the area underneath the barrel. Now that would be pretty easy if the barrel was oriented differently. Like if you look at the shape of it, right now the cylinder is on its side, which means that the pressure forces are going to be acting in a whole variety of directions, and the magnitude on the underside is going to be changing because the depth is going to be changing. So we would have these pressure forces acting in different directions, and the pressure forces on the bottom would be bigger than the pressure forces when you go up a little bit. So it would be tricky to compare what's going from above and what's going from beneath. So I think instead the easiest thing to do is calculate the buoyant force just on the basis of the volume of water that's being displaced. So when we do that, we get the buoyant force is 55 kilonewtons. Now will it sink or will it float? We have to compare it to the weight, and so weight is mass times g. And as I was walking around, I got a good question about g. Is the gravitational constant the same if an object is submerged? And it is. And I have actually a homework problem that you didn't get this semester, but it's a really interesting one about what if you have a scale, and it's a waterproof scale, and you're measuring something like a concrete cylinder, and then you move the cylinder and the scale underwater. Then now all of a sudden the scale is saying something different. And so the before reading and the after reading, could you calculate what is the density of the object by the before and the after? And so it's like a tricky question when you look at it, the issue from the standpoint of that scale it will give you a different measurement underneath the water, but it's not because the mass changed, it's because the buoyant force is taking effect when you submerge it. So anyway, the answer is yes, g is the same whether or not the object is submerged or in the air, the gravitational constant stays the same. So our comparison here, looking at the buoyant force versus the weight, since the buoyant force is greater than the weight, it will float. And so it's going to move up to the surface, and then it'll stop rising when it achieves equilibrium. So it's not going to be very deeply submerged. Looking at the ratio of the weight and the buoyant force right now, it's going to be floating more than halfway out of the water. The other way to look at it is just to look at the unit weight of the barrel, and we can calculate the unit weight for any object, whether it's a solid or a liquid. It's just the weight of that divided by the volume that it occupies, and since the unit weight of the water is greater than the unit weight of the barrel, that's another way that we could go through the reasoning and determine that it's going to float. Is just the unit weight of the object or the density of the object. It's not going to sink if it's lighter than the fluid that it's surrounded by. Okay, any questions about that example? All right. So here we have a picture of a boat going through the water, and it looks like a nice sunny day. Great hobby for people with plenty of money. Boats are very expensive. I don't have a nice big sailboat like this, but it looks like these guys are having a great time. Why do you suppose they're all sitting on the edge of the boat? Counterbalance. Exactly right. Yeah, and if you look underneath the water line, you can kind of see just through the water a little bit of a indication that there's something going on underneath the water line that we can't quite see. Like there's a long ballast. I'm not a sailor, so I don't know what they call that, but there's like a lot of weight beneath the water line that's also helping to keep the boat from tipping over. You don't win a sailing race if your boat tips over. And so at the same time, the straighter it is, like if they can get it, instead of leaning down a lot, if they can get it to go a little bit straighter, and they may get some additional speed out of that because they'll have a greater cross-section of the sail interacting with the wind, where if it's over sideways, they're not going to get as much wind going across the sail. So what we're going to be talking about today is their calculations that will allow you to predict whether an object is going to float in stability or whether it's unstable and if it's going to tip over. And maybe you've seen pictures of some of the new cruise ships, like the really big ones that can carry like 5,000 or 6,000 passengers. They look so tall. Or maybe you've seen pictures of container ships that carry cargo between Asia and the United States. And they're also just loaded so tall that you wonder how can they not tip over, especially when it comes to rough seas and a storm. So we're going to go through the equations that allow us to calculate whether something is stable or unstable. So compare and contrast a submarine, where you can see that these sailors are standing on top of the submarine, and it's not like spinning over. They're not having a log ride contest in the same way that this kid is. I mean, the game of this is to see how long you can stay on something that's naturally not very stable. And so there's some real similarities there. They're both floating on the surface. They've achieved equilibrium in terms of if they're going up or if they're going down. They're both cylindrical. They both have people standing on the top. So the sailors aren't having to struggle to keep their balance because the submarine has been designed to be stable as it floats. Maybe also it being bigger helps too. The inertia of it starting to tip, the inertia against any kind of rotation means that it's going to tip more slowly compared to a smaller log. If it was a larger log, then it would be easier for that kid to keep his balance than a small diameter log. So let's take a look at the fundamentals here. If we have some shape that's submerged, and you can see that this shape has a little bit of extra weight on one side of its cross-section. That extra weight is a ballast that's there intentionally to make it so that it floats in a stable way, or that that the bottom of this, they put the ballast in the part that they always want to be on the bottom. And so if people are going to be inside of this shape, now they can put computers and a periscope and bunks and stuff, and everything isn't going to be tossed when it just starts rotating. Because G, the center of gravity, is below C, the center of buoyancy. Now the positioning of the center of buoyancy is only dependent on the shape of the object. So the center of buoyancy is determined by the forces that are acting on the outside of it. So what's happening on the inside has no effect on the location of the buoyancy. But what's going on the inside of this shape does have an effect on where the center of gravity is located. And so you can see that the center of gravity is a little bit lower than the center of buoyancy, because if you take the average of the weight of whatever this cylinder is made out of, let's say it's maybe made out of metal or something. So the metal has a little bit of mass, but then this concentration of the weight at the bottom brings the center of gravity below the centroid of a circle. So because G is below C, that means that it's always going to be stable. Eventually, it'll come back into an equilibrium. So keep in mind that the center of buoyancy depends on the outside shape, whereas the center of gravity depends on the mass of the object and what's on the inside. So it's stable because if we tried to tip this, like if you were swimming around underneath and you tipped it and caused like a disturbance in the equilibrium that it's floating in right now, it will right itself. And so let's take that case C here. It's the same object, but we've just tipped it now. So the center of buoyancy, C, is going to push it up. The center of gravity is going down. Think about if you take a piece of paper and you put your fingers on two spots and you push up on C and down on G. So it's going to cause a rotation of the object, and if I continue to push up with C and down with G, I'm still pushing right now, but it's not moving anymore, because you get to the point where G is below C and those two forces are canceling each other out in terms of their direction. And so it's going to stop rotating when you have one beneath the other. Now, this one in the middle, we'd call that neutrally stable, because it's not necessarily going to have that same what's called a righting couple, a couple that would cause it to become righted. If I rotate it, then it has no reason to rotate back to its original position, that one in the center. The one on the edge is currently unstable, but because of that righting couple, meaning one force going up, another force going down, it would come back into the original equilibrium and become stable again. Does everybody understand the idea of that righting couple? The two forces that are acting in opposite directions, but then when they are one above the other, it's not going to cause any further rotation. So this is definitely stable. One thing that we could say, if we're like creating rules, we could say that if G is below C, the object will be stable. Like if you're going to make a ship or a submarine, and you make it so that your center of gravity is below the center of buoyancy, then it will be stable. If you splash it with a wave and it temporarily tips over, it will come back into equilibrium. That's one rule. If G is below C, it's stable. But that's not the only thing that can make for a stable vessel. Here is a ship, and we have these same definitions as before. C is the center of buoyancy. G is the center of gravity. Now this time, the center of gravity is above the center of buoyancy, but as I'm going to show you in just a minute, it's still stable. It's still stable because of what happens when it begins to tip over. Now, before we get into that, let's think about why is G above C. Any thoughts? What could bring the center of gravity above the center of buoyancy?
More mass above the water.
More mass above the waterline. Exactly right. That's right. So if we have a tall ship, the location of the center of gravity depends on the boat and where is the mass in the boat. So if you've got all these cabins and cargo above the waterline, then that's going to bring the center of gravity higher and higher. So if you keep stacking more stuff on the boat, you're making it more and more unstable because you're raising the center of gravity higher and higher. But there is a limit. You know, if you pile it too high, it's unstable, but it can be stable to have G above C. So let me explain why that is. If we tip over the ship, then the center of buoyancy is going to change. Because look at the shape of the hull. Right now, the center of buoyancy is in the middle of the boat because the boat's straight up and down. But if you tip over the boat, like we just did here, the location of the center of buoyancy is now shifted to the right. For now, ignore A, B, D, E. Just think about how has C changed location. C has shifted over to the right. So why? Any thoughts on why the center of buoyancy is different when the ship is tipped over compared to when the ship was just floating upright?
There's more mass on the right side.
There's more something on the right side. It's not mass though. More volume. Take it a little bit further. More volume what?
Under the water.
Under the water. Very good. So the volume of the ship stayed the same. The mass of the ship stayed the same. But when the ship tipped over to the right, now the submerged volume on the right side is more than the submerged volume on the left side. So you see this little triangle A, O, B? That volume used to be below the waterline. But when the ship tipped over, now that volume that used to be on the left is on the right. That's how much added volume there is, because you can just kind of tell by inspection that, I don't know, there's more volume on the right side than there is on the left. And so C is the center of buoyancy. And the center of buoyancy, its location is determined by, you know, what's the submerged cross-sectional area on either side. So tipping the ship over shifted C to the right. Does everybody see that? I mean, it's not an accident that they designed the ship with this particular shape. The shape of the hull helps them to slice through the water, but also the shape of the hull in part is designed so that when the ship begins to tip over, that there's more volume on the side that was tipped over, so that we have a righting couple. Do you remember when we talked about a righting couple here? Put your finger on the page and you go up with one force, down with the other, and it brings it back into equilibrium. Okay, so now imagine, if you can, that you have a paper cutout of the ship. And you push down with G and up with C. What's it going to do? It's going to tip it back up again. And so as it tips back up, C will shift back to the center, and then it's straight up and down. And so you can continue to push up with the buoyancy. So that is applied at C. You can continue to push up at C and down at G, but when they're on top of each other, then that's not going to do anything about tipping from the left and from the right. It's only when some external force, like wind or waves, causes it to shift one direction that then there's the righting couple that will cause it to go back into equilibrium. Everybody with me so far about like the cause and effect of it beginning to tip? Okay, so then let's go through this technical definition here of the metacenter. M, which you can see in the one where it tipped over, M is, there's this certain point where the center of buoyancy points towards the metacenter, and if we tipped it over a little bit more, the center of buoyancy would shift a little bit further to the right. And the direction of C would point up at the metacenter. And so kind of like the metacenter is the point of intersection of all of the buoyant forces as you go through a range of motion. So we tip it over really far, then maybe the C is over here, but it's pointing towards the metacenter. You tip it less far, it's still pointing towards the metacenter. So the metacenter is the intersection of all the lines of action for the buoyant force as it goes through that, that rotation. So C points towards M. That's the metacenter. So this ship is stable, even though the center of gravity is above the center of buoyancy. So the earlier criteria I told you is a ship is stable if the center, based on this example, it's stable if G is below C, but it can be stable if G is above C, but there are limits. And so we're looking for a new rule of, like, how can it be stable when G is above C? And the answer is, if the metacenter is above the center of gravity, the object is stable. But if the metacenter is below the center of gravity, then it's not stable. All right, so what determines where the metacenter is located?
Is it the center of mass?
It's the center of all of the volumes. Remember, C, the center of buoyancy, is determined by the submerged volume. And so the location of the metacenter comes from C, and C is depending on, like, volume location. So that's what's the water being displaced. G is dependent on mass. So if we load the ship with more and more cargo, what does that do to the metacenter if we are adding more mass? The metacenter, well, indirectly it may, but the metacenter is unaffected by loading mass onto it. Loading the extra mass changed G. It changes the center of gravity. So the center of gravity is directly affected by the mass of the object. The metacenter is affected by the submerged volume. So, like, what would make this unstable? Right now it's stable, but what would make it unstable? Well, if we piled on more and more weight, what would happen is the center of gravity would go higher and higher. So if you piled on so much weight that now the center of gravity is above the metacenter, then the problem is it can never recover from tipping over. That's what makes it unstable, is that righting couple is eliminated if the center of gravity is above the metacenter. Complicated stuff. You'll get some practice that'll help to make it a little bit more understandable. So if G is above M, it's unstable. G is below M, it's stable. In the equation that you use to calculate the distance GM, and what we're looking for stability is a positive GM, we're going to need to use the area moment of inertia of the shape that is described by the waterline of the vessel. So just to make it really plain, I've got this barge pictured, and the width of the barge, the smaller of the two dimensions, is B. The length of the barge, A, is the longer of the two dimensions. So you've probably seen barges going up and down the Ohio River, and they're much longer than they are wide. And so whatever the length versus the width, whichever one is the smallest, is the term that you cube. And it's the shape of the water up against the hole that you'd use. And so just for simplicity's sake, we're using a rectangular shape. But you can calculate an area moment of inertia. What we're wondering is, how easily does it tip over? So a big area moment of inertia is going to help give you stability. Think about if you have a really wide barge. It's not likely to tip over if this barge is really wide. But what if it's really narrow? Like, what kind of a boat have you ever ridden in and you almost like tip over just getting in it? Like a canoe, right? A canoe is really narrow. And so that's what makes it so tricky to stay upright, is it has a very small area moment of inertia. What did the Hawaiians do to make it so that their canoes tip over less? they add that outrigger arm on it, and so by adding that extra width, essentially it makes it so it's less prone to tipping over because they've dramatically increased the area moment of inertia. So they've increased that A parameter. No, I'm sorry, they've increased the B, the narrower of the two, by adding that arm on the side. Okay, so this is how you interpret and apply area moment of inertia. Now here's the formula for metacentric height, GM. GM just means the distance between G and M, but we call that distance the metacentric height. So we've just talked about how you determine the area moment of inertia. V is talking about the submerged volume. So that's just the volume underneath the waterline. And then CG is the distance between the center of buoyancy and the center of gravity. And usually you can determine that by information about how the ship is loaded, information about how deeply the ship is beneath the waterline. So you'll have some dimensions that will help you to determine CG. And you calculate GM, and if it's a positive value, meaning that I divided by V is bigger than CG, then that means it's going to float and it's stable. So think about what gives you a big metacentric height. What gives you a big metacentric height is a big area moment of inertia. So if we maximize the width of the barge, it's less likely to tip over compared to if it's a very narrow barge. So a narrow barge would give us a small b, which gives us a small area moment of inertia I. And if I is small, then this whole first term isn't going to be very big compared to the CG. So a wide ship is more stable against tipping over. Now look at CG. If you have a really large CG, then that's another problem that's going to lend itself towards instability. So if you have the center of gravity being really high above C because you've stacked so much cargo on top of the ship and you keep bringing the center of gravity higher and higher. So when you stand up in a boat, like your canoe, when you stand up in your canoe, you've now taken the center of mass really high. If you sit down in the canoe, now it's less likely to tip over because your center of mass is lower in the ship. So you can kind of just intuitively think about what are some of the things you've observed out there in the world about metacentric height, and it all fits into the equation.
Now, in the example of the boat, the volume, is the volume same even though it tipped? The submerged volume will be the same even though it's a different...
Good question, yeah. So when the boat tips over, the boat still weighs the same. So the mass hasn't changed, and so the volume displaced will have to stay the same. So it's still going to be in equilibrium in terms of the buoyant force and the weight will equal each other. It's just where the volume is located is changing. So it's not the magnitude of the volume, it's the location of the volume is shifted over to the right, which creates that righting couple.
So the area moment of inertia and the volume is a constant?
Yeah.
So the only one we worry about is the CG value.
Yeah, and when you calculate metacentric height, you'll calculate it based on when it hasn't started tipping over yet. Yeah. You'll calculate that when it's straight up and down. And I have an in-class exercise that I'm going to give you to practice this. We're going to consider a barge, and you can see the dimensions of it there. And going through a step-by-step to try and assess whether it's going to tip over or whether it's stable.
I think I'm gonna need your help with that.
Trust somebody who's in Italy. Well, hopefully we got till Friday, then it cools off like 74, then it should be a straight drop.
Okay, let's go through this step by step, and then I have to remember to cover this point that it's not just calculating GM to be positive. The other thing is if there's more weight on board than can be supported, then it's also going to sink. You know, like if the depth of submergence, based on the mass that you're adding, if it told you that it needed to be submerged to a depth of 3 meters, but the barge itself only has 2.44 meters on the edge, then we'd be in trouble there as well. All right. The weight of the barge is just based on the mass that they gave us, so 1.7 meganewtons for the weight, and if it's floating in equilibrium, then the buoyant force and the weight are equal. Then to find the depth of submergence, this parameter D, we know all of the dimensions in the submerged volume except for D. We know the width of the barge, we know its length is 15.25 meters, and so D will be the only unknown. When we solve for that, 1.978 meters is the depth of submergence. Now the sketch of the barge from the top view, I asked you to do that just so that you don't accidentally use 6 and 2.44 in the area moment of inertia. That would be a mistake, and it would be an easy one to make because till now, anytime we've used area moment of inertia, we have been talking about some vertical projection. And so maybe your first reflex would be, okay, this is A, this is B cubed, but that's the wrong approach. We need to do a sketch of the waterline. So from a top view, the barge looks like 6 meters wide and 15.25 meters in length. And so that helps us then to address E, which is the area moment of inertia of the barge, 274.5 meters to the fourth. The distance CG we get by drawing where is the center of buoyancy. So if it sits a depth of 1.978 meters, if that's from the water line to the bottom edge, then the center of buoyancy is going to be half of that. So just 1.978 divided by 2 gives 0.989 meters, and then from the original dimensions that are given, we know that from the top edge to the bottom edge is 2.44 meters. And so what we need to know is how much extra distance is there from the water line up to G. And so we get that by, we know D, we calculated that much earlier, what D is. And so once we calculate D, then you can calculate the distance from G to the water line. And that is 0.462 meters. So altogether, the net distance between C and G is, where did I do that? 1.451 meters. So in the end, GM, the metacentric height, is positive, which means this is going to be a stable floating body. So if we tip it over, then it's going to right itself again. Now there's limits to that. And if we tip it over so much that now this edge is beneath the water line and it starts taking on additional weight and losing buoyancy, then it's not stable any longer. But if we just kind of nudge it a little bit and don't quite take it so that this edge is below the water line, then it'll come back into equilibrium. It'll float upright. Okay, any questions about that example? No? Let's see, we got a few minutes we won't actually solve this one, but I want to show it to you and we'll talk about it because it's kind of an interesting, thought-provoking problem. Find the forces required to hold the curved gate steady. So here's a curved gate. And what makes this example a little bit tricky is that the gate is above the water line. Do you see how here we have atmospheric pressure? And so the water pressure at the interface is 0. And as you go down through, oh, it's not water. This is something else. We know the unit weight is 50 pounds force per cubic foot. So this is lighter than water, but still the principle holds true that as you go down through the fluid, the pressure increases. But then as you go up through the fluid, the pressure decreases. And so here, the pressure is 0 in the liquid. And then as we start going up through the liquid, the pressure is negative in terms of gauge. It's not necessarily negative in absolute terms, but it's a negative gauge pressure. So what's the direction of the force? Do you have an instinct for, like this gate, what is the water doing to that gate? What direction is it pushing or pulling on that gate? It's sucking the gate in. That's right. So this is a tricky problem because we normally think of the pressure acting against the gate, but here it's drawing the gate inward. And so if you wanted to find the vertical force, what you'd do is you'd look at the weight of the water not above the gate, but you'd look at the weight of the water beneath the gate until you got to the water line. And so by the water line, what we mean is the location where there's now 0 pressure. So how far beneath that gate do you have to go to get to 0 pressure? And so the weight of the water would be that quarter circle volume. You know, it says it's 2 feet wide, so it's like a quarter circle with some 2 foot wide depth, and so it's like a pie shape. And then there's also a rectangular shape, 1 foot of depth, 2 feet of width, and then 3 feet of length. And the horizontal force, we still follow the vertical projection approach, but this time, instead of pushing on the gate, the force would be to the right because the pressure is negative. So I just wanted to show you this kind of like head scratcher example just to, I don't know, show you another trick that could be up my sleeve. Anytime you know, you've got an exam on the horizon, you have to be wondering, how is he going to try and trick me? Because that's what it's really all about in the end. Tricking and disappointing students.
Of course.
So the exam is Thursday, 11 o'clock. You'll have 75 minutes. The equation sheet's available now, so let me know if you've got any questions. The homework solution is also available, and so I'd encourage you to go through that. See you Thursday.
So in the lab,